Now that we've talked a lot about calculations, one of the things that we'll have to talk about next is what we do with the answers and how we find out how close we were to correct. An important calculation that you'll do off and on here and there, and I'd say more so toward the middle of the year and when we're doing more mathematical based labs, but also early in the year, is calculating something called percent error. Percent error will help you to find out how far off from correct you were in your work and in your calculations, and to see how well you did in the lab, essentially. It's important to know that there are very, very few instances in my class when your overall score on the lab is based at all, or even largely, on your percent error, whether or not you were close or off by a little or off by a lot. Often that has very little bearing, if any, on your actual score on the lab. So the importance is not that you get perfect results every time, but that you can show what your results were, that you can calculate how close you were to perfect or correct, and that we can kind of try to figure out for next time what we would do differently in order to get better results. Science isn't about being right the first time, it's about understanding why you weren't right the first time and figuring out a way to get a better result in the future. So as we're figuring out percent error and talking about your error, it's not quite as serious as it sounds at times. Percent error is calculated based on two values. The first is called the experimental value. The experimental value is the answer or the measurement that comes from a lab or experiment. Generally, this would be something that you would measure or something that you would calculate from something that you would measure in class, or possibly a value that would come out of a story problem. So it might be that you go into the lab, make measurements, do calculations, and get your own experimental value. It might also be that you'll read a story problem. You know, Jane and John Doe make an experiment, and they measure this, and they measure this, and they calculate this. It might be that someone else in a fictitious story problem did the measuring and the work themselves, and now you're using their values as experimental. It should come from somebody's work, hopefully your own. An experimental value is compared then to the second one you see here, called literature value. The literature value is the accepted correct target value that comes from a trusted source. Usually that would be something like a reference book or a reference table. There are several important ones for reference tables in the back of your lab manual. You might get it off your periodic table, which if you don't have it yet, you'll be getting soon. Or you might just get it from a teacher who gets it from a source that maybe you haven't seen, but they go and look up online, or they have a book for it. So a literature value is sort of the correct answer. Of course, the goal would be that your experimental value and your literature value would be the same, or very, very close to the same. When they're far apart, that means there's probably something wrong with your procedure, or your measuring technique, or maybe your calculations. And we want to try to figure out what it is. So experimental value is your measurement or value, and the literature value is the correct one. To calculate what we call percent error, which is really the goal and the key here, we calculate it this way. Percent error is found by subtracting experimental value minus literature value. And you notice here on the top of this equation that they're in brackets or square lines. Of course, hopefully you recognize these square lines on each side to represent absolute values. So we would, if experimental value minus literature value gives us a negative number, we simply drop the negative sign. And if experimental value minus literature value gives us a positive number, then we would keep it positive. The key being here, we don't care, per se, if your answer was too high or too low when we're calculating percent error. So there should be no negative answers. Now, we only want to know how far off you were. We don't necessarily care at this point if you were too high or too low. There will come times when we want to figure out if you were high or low and figure out why. Sometimes we figure out the solutions differently. But for now, percent error is always a positive answer. So use absolute value on the top here after you subtract. Then you divide by the literature value. So you'll actually use that literature value in here twice. And then at the end, take it all times 100 to turn it into a percentage. This is pretty typical when calculating percentages of any kind. Just take it times 100 at the end. So experimental minus literature divided by literature times 100. And then the absolute value should come in there after you subtract, but it really could come in at any time in the problem, as long as at the end your answer is not negative. So a percent error then, perfect, would be 0% error, because the two numbers on the top would be the same, and when you subtract, you would get 0 divided by anything times 100 would give you 0% error. So perfect is 0% error, which kind of makes sense. Let's go through an example. By the way, this equation isn't one you necessarily have to memorize, because it's usually on the sideboard in class, but you want to keep it close and put it in your notes, because you will obviously always be solving problems sitting in my room. You might be doing them somewhere else, or if you're not in my class and you're watching this video, it might not be the case that this equation is readily available to you. I should note you might see some places where this equation is written with the top two values switched, literature minus experimental. The key is that it doesn't make a bit of difference. When you do absolute value, it cancels out any difference that it makes by subtracting them in whatever order you want. But it's key that the bottom number here be literature value. So here's an example with that equation back at the top. Let's say we were doing a lab on density, and you were to calculate an experimental value from your work in the lab of a density of 8.77 grams per cubic centimeter. I think we're doing densities here for nickel, if I remember right. But let's say your experimental value was 8.77 grams per cubic centimeter. And we went to the back of our lab manual and we looked up the literature density for nickel as 8.908 grams per cubic centimeter. Well, you can see those two quantities are fairly similar, but they're not quite the same. So we want to calculate, using our equation, what was the percent error for this part of your experiment, for your work here. So percent error, we'll say, will be experimental, which you found is 8.77. I'm just going to draw my numerator to denominator line here. Experimental value was 8.77 grams per cubic centimeter, and you always want to show units in your work here, minus the literature value up here, which was given to me as 8.908 grams per cubic centimeter. And then on the bottom, I'm going to use literature value, which is 8.908 again. So that same number shows up twice. And don't forget, on the top, we want to use absolute value. So I'm going to put absolute value symbols on there and then times 100. Now, we just got done going through significant figures in previous videos, how we round when we're doing multiplication and division using significant figures, and then how we round when subtracting and adding using decimal places. So actually we have both here. We'll need to subtract on the top first and use the rules for subtraction, and then we'll divide and use the rules for division. So to find that, let's do the top part first. 8.77 minus 8.908. I'm going to bring up my calculator and we'll punch that in real quick. 8.77 minus 8.908 gives me negative 0.138. Now, when I'm subtracting, I want to remember to round my answer to have as many decimal places as the original value with the fewest. In this case, 8.77 has 2 decimal places and 8.908 has 3. So the fewer of those is 2. And so in subtracting those two answers, I want to round my answer off from the calculator here to have 2 decimal places. And also, I want to drop the negative sign because I've got those absolute value symbols here. So negative 0.138, I get rid of that negative sign, and then I'll get rid of that first. And, oops, what the heck did I do? That doesn't work. Let's go back up. And so negative 0.138 becomes positive 0.138, and then we want to round that off to have 2 decimal places, which would be, hopefully you could see that, as 0.14. 2 decimal places again because this has 8.77 has 2 decimal places. So just in my subtraction, I'm going to take that, subtract it, round it, and drop the negative sign, and that gives me on the top 0.14 grams per cubic centimeter. So I subtracted, I rounded, and I did the absolute value. Now on the bottom, I still have 8.908. grams per cubic centimeter. We haven't done anything with that yet, times 100. So let's go ahead and divide next. 0.14 divided by 8.908. Let's bring that calculator back up. 0.14 divided by 8.908. And my calculator gives me 0.015716. Okay. Now, when we're dividing, we want to round it off based on significant figures. And the fewest significant figures of these two values is on the top, 2, right? Not decimal places, which is 2 also, but 2 significant figures is the key. 0.14, the 1 and the 4 are significant, so 2 significant figures in my answer. When I round this off to have 2 significant figures, I'm going to go to 0.01, and that 5 will round up to a 6, right? So 0.016 is my overall answer, and then we'll take that times 100. 0.016. Now notice when we divided this, the grams per cubic centimeter is a unit that would cancel off. And so those sort of disappear and don't show up in my final answer. You can go ahead and cancel them over here if you'd like, but they disappear because they're the same top and bottom. And then taking this times 100. Now this is important. Taking this times 100 here in the calculation, we're not going to round our answer off to one significant figure just because the number 100 seems to have one significant figure. When we're multiplying and following rules of significant figures, we usually want to follow those based on the numbers that we measure, quantities that we get from our work. taking it times 100 here isn't a 100 that we measured anywhere in lab or in class. That's a quantity that's used just to adjust this to a percentage. So when you're using 100 in an equation like this, treat this 100 at the beginning of our equation and throughout your work, as we can sort of thinking of it as having infinite significant figures. I'm not sure that's quite the accurate way to call it, but we're going to say that here anyway. In other words, don't limit your answer around it based on that 100. We have two significant figures in 0.016, and we're going to keep 2 in our final answer. So when we multiply that out, we get 1.6%. 1.6% error. That's pretty good. You can think about that as more or less being 98.4% good or 98.4% accurate, which if you got that on a test or quiz or for your grade, that'd be awesome. So 1.6% error is pretty impressive. And we hope for it to be small. There will be labs where you'll get a good percent error like this, and there'll also be labs where your percent error might be in the 50s or 80s or hundreds, or I've seen labs where people will have just dramatically goofed up numbers and they'll have percent errors well into the several hundreds. Hopefully we can figure out why, and in many labs we do 2 trials. In case you have one kind of go funky, you'll have one to sort of fall back on as not so bad. So that's one example of how to find percent error. We subtracted, we used the rounding rules for subtraction on the top and got 0.14, and then we divided by our literature value, 8.908, and used our dividing rules of significant figures to get our answer of 0.016. Took that times 100 for an answer of 1.6%. So we use 2 different significant figure rules, and it's important to keep those in mind in any work that you do. Order of operations still follows. Here we did the subtraction, then we did the division, just like you would do in order of operations, and then there are those rules that you follow at each step. So I hope that helps. You understand percent error, and if you have other questions about it, I'll try to post another video or 2 with percent error problems. And if you have it figured out, great. Go for it from there and continue to use this equation. Thanks.